The implicit grant flow is fundamentally broken for public clients like single-page applications and mobile apps. The core vulnerability is the exposure of the access token in the browser history or through referrer headers, making it susceptible to interception via cross-site scripting attacks. Since public clients cannot securely store a client secret, the implicit flow offered a workaround, but at a severe security cost. We need a mechanism that proves the client requesting the token is the same client that initiated the authorization request, even without a secret. This is where Proof Key for Code Exchange, or PKCE, steps in. PKCE transforms the standard authorization code flow into a secure option for environments where client secrets are impractical or impossible to protect. We are detailing the exact cryptographic steps required to implement this correctly, starting with the initial key generation. PKCE introduces two new parameters, the Code Verifier and the Code Challenge. The Code Verifier is a high-entropy, cryptographically random string generated by the client for each authorization attempt. It must be between 43 and 128 octets long after Base64 URL encoding. The Code Challenge is a transformation of this verifier, typically using SHA256 hashing. The crucial point is that the client keeps the verifier secret until the final token exchange. This ensures that even if an attacker intercepts the authorization code, they cannot complete the final step without possessing the original non-hashed verifier string. This binding mechanism prevents the authorization code from being redeemed by a malicious third party, effectively mitigating the code interception attack vector common in public clients.
The client application initiates the process by generating the code verifier. This must be done using a cryptographically secure pseudo-random number generator, ensuring sufficient randomness. For example, in JavaScript environments, use window.crypto.getRandomValues. Once the verifier string is generated, the client calculates the code challenge. The standard method is S256, which involves taking the SHA256 hash of the verifier string and then Base64 URL encoding the resulting hash digest. This two-step transformation is critical. The client must store the original code verifier locally, typically in session storage or memory, until the token exchange is complete. This storage must be transient and protected from cross-origin access. The client now redirects the user agent to the authorization server's authorization endpoint. This request includes the standard OAuth parameters, client_ID, redirect_URI, and scope. Crucially, we append the two new PKCE parameters. First, the code challenge, which is the Base64 URL encoded SHA256 hash we just calculated. Second, the code challenge underscore method, which must be set to S256, explicitly signaling to the authorization server that SHA256 hashing was used. The authorization server receives this request and stores the code challenge alongside the pending authorization session. It does not yet validate the challenge. It simply records it for later comparison. After the user successfully authenticates and grants consent, the authorization server issues the authorization code. This code is returned to the client via the specified redirect URI, typically as a query parameter. This is the point where the code is most vulnerable to interception, perhaps through a compromised browser extension or a malicious application registered on the device. However, because we are using PKCE, the intercepted code is useless to the attacker. The authorization server has bound this specific authorization code to the code challenge received in the initial request. The attacker possesses the code, but not the original code verifier required for the next step.
Upon receiving the authorization code, the client immediately initiates the token exchange by making a direct back-channel post request to the authorization server's token endpoint. This request is server-to-server, bypassing the browser entirely. The request body must contain the grant underscore type set to authorization underscore code, the received code, and the redirect underscore URI used previously. The critical PKCE addition here is the code underscore verifier parameter. This is the original high-entropy random string that the client generated in the first step and kept secret. This is the moment of truth where the client proves its identity without relying on a static client secret. The authorization server receives the token exchange request containing the code verifier. The server performs the validation in two steps. First, it retrieves the stored code challenge associated with the provided authorization code. Second, the server applies the specified code challenge method S256 to the received code verifier. It calculates the SHA256 hash of the verifier and then Base64 URL encodes the result. If this newly calculated value exactly matches the stored code challenge, the validation succeeds. If the values do not match, or if the code verifier is missing, the server must reject the request with an invalid_grant error. This cryptographic comparison is the core security mechanism of PKCE. Upon successful validation, the authorization server issues the access token, and optionally a refresh token to the client. Since this exchange happened over a secure backchannel, typically transport layer security, the tokens are delivered directly to the client application without exposure in the browser URL or history. The client application, whether it is a single-page application or a native mobile app, can now use the access token to call protected resource APIs. The client must ensure that the access token is stored securely, preferably in memory for SPAs, or using platform-specific secure storage mechanisms for mobile applications, minimizing the risk of local compromise.
Implementing the SHA256 challenge method requires strict adherence to the RFC 7636 specification regarding encoding. The code verifier must be Base64 URL encoded without padding before hashing. The standard Base64 encoding uses plus signs and forward slashes, which are problematic in URLs. Base64 URL encoding replaces plus with minus and forward slash with underscore, and omits trailing equal signs padding. After hashing the verifier using SHA256, the resulting 32-byte hash digest must also be Base64 URL encoded without padding to form the code challenge. Using standard Base64 encoding at either stage will result in a validation failure at the authorization server. Developers must use libraries that explicitly support Base64 URL safe encoding. PKCE is mandatory for all public clients. It effectively eliminates the threat of authorization code interception attacks, which is the primary vulnerability when using the authorization code flow without a client secret. For system analysts, the deployment checklist includes ensuring the code verifier is generated per transaction, enforcing S256 as the only acceptable challenge method, and configuring the authorization server to reject requests using the plain challenge method. Furthermore, the authorization server must enforce a strict time limit on the authorization code validity to minimize the window of opportunity for replay attacks, even if the code is intercepted. This robust flow ensures secure delegation of authority in untrusted environments.